Okay, here we are, video 4. Video 4, that's Thermokinetics video 4 and Kinetics video 1. So this is where we're beginning today. Kinetics 1, video 4, night chemistry, thermochemistry, and kinetics unit. Let's get straight to it then. And we're back. Kinetics is all about reaction rates. And where we're getting at. What is a rate law? That's our central question. Can you think of 5 examples of rates from your daily life? Rates of change. Based on these examples, what do you think a rate is? What's a rate? What do you think rates have to do with chemistry? You may have already gleaned it from this point. Anyway, take a moment, pause, and let's consider it. So, chemical reaction rates, reaction kinetics. If you didn't already think of some, rates of change of displacement over time, that'd be velocity. Distance over time, speed, right? Rates of consumption, how fast you consume a food, right? How fast your food on your plate disappears. Right? Typing rate, typing words per minute. Let's see. Your running speed, like speeds and rates are all rates of change. Rates are how fast something changes over a period of time. So in terms of reaction, it applies pretty specifically in chemistry because reactions can occur at different rates. Reactions, remember, are reactants turning into products, rearranging molecules, turning into products. So we're going to look at the what makes a reaction, what makes a reaction occur in the first place, and then we're going to tie that back into how to make a reaction go faster. Reaction kinetics. So what's a rate? What are some examples of rates you can take from your daily life? Right? We've looked at some of these before. We just mentioned some rates of change of location, speed, distance, right? Velocity. What do you think rates have to do with chemistry? Well, that'd be reaction rates. A rate is how fast or slow something happens over time. Rate does not mean how fast it will take something for everything to finish. It's just how long it's taking. That's not how fast it takes you to go from your house to school. It's the rate of change of you. It's your speed that you took on the way to get there. How fast are you going on average in the in-between time? It's not a completion of everything, okay? Collision theory. Now, I'm going to pause time for a second because I want to show you something. There is actually a note-taking device for you to fill in while you're taking these notes. Perhaps you could have this video in an open tab or an open window and then make a smaller minimized window be the note-taking apparatus, which I provided for you for this unit only. It's because it was already previously made. I didn't get too wild here. So by the time you watch this video, Kinetics Day 1, where you've clicked on this video, will actually also have this Google document for reaction rate notes for you to write or type. You could print it off and write it, or you could just type directly into the boxes. The boxes will expand as you go. So of course you can do that. You can change the font size because this will be your document with your name on it up in the upper, in the actual title of the notes. So pause right now, go open this Google Doc and type these notes in according to the slides that we're on, right? So we have a note about rates. That's what a rate is. And collision theory, the definition, that's where we left off. So go get that note right now, okay? Because I'm not stopping. You pause because it's a video, and then you can fill it in a moment. Ready, set, go now. Okay, cool. Collision theory is that the rate of a chemical reaction depends on how many collisions, bumps, the atoms make with each other. So the reaction is reactants turning into products. I'm tired of being blurry. If a reaction is where reactants transform without destroying any matter or energy into products, brand new thing. Let me do it the other way. Reactants transform into a new products, new arrangement of molecules. In order for the reactants to transform into a product, reactant molecules have to collide into each other so that the bonds can break and then reform. So a couple things have to occur. There must be collision. Collision theory is the theory that reactions depend on these collisions to occur. Okay. But on top of collisions, we gotta also think about in the back of your mind that a reaction would take place if the collision is the right kind of collision, has the right amount of energy, when they collide to break bonds and then to reform new bonds. So it has to be enough energy to break and reform because there's energy stored in those bonds. And then of any bond, there's energy stored in it. So when you talk about it takes energy to break a bond, that means you have to have energy that's breaking the energy that's stored in the bond, right? Okay, so it's releasing that energy. So you have to input the energy to break it first. Anyway, so bonds need to be broken. So collisions of enough energy to break the bonds and then reform new ones. They have to be oriented. They have to be close enough in space. There's got to be enough of them. The faster they move, the harder they collide, the more energy that they collide with. So a lot of factors can come at play in terms of causing a reaction. Collision theory states that we need to have collisions to make reactions occur, to turn reactants into products. What are some things that we as scientists can do to make more collisions happen? That's the focus. If we increase the number of collisions in a smaller amount of time, the rate increases, and that's where we're living right now. It's the reaction rate. Reaction rate kinetics is that it's all about collisions do the thing, increase collisions. What can increase collisions? That's how we're going to go with it from there. So remember, you're taking these notes so you can pause at any moment while I'm talking to do this. Once again, collision theory states that basically atoms must collide, molecules must collide in order for the reaction to take place. Also, there are three things that this entails to include. Reaction particles must collide with each other. That's one. Two, collisions must be of enough energy to overcome this energy barrier called the activation energy. We've seen that before. More on this in some future slides. And the reactants must form new bonds to produce products. So, collisions with enough energy to break reactant bonds, form new product bonds, and then new product bonds must be and stay formed, at least for a moment, of course. They can unform, they can reverse reactions, they can produce secondary reactions, of course, but that's neither here nor there. The new bonds must be produced. This is three things for a reaction to occur. Get them down. Activation energy is defined as the minimum energy required to bring about a chemical reaction. It's the energy barrier that dictates the collision's results. If there were no such thing as activation energy, life would be difficult because reactions that could occur would occur spontaneously, without purpose. Snapping my fingers, I would ignite gases that exist in the air just in less than toxic amounts, in just typical amounts. They would ignite into a fire. So that would not be, obviously not be very good. Just snapping your fingers, that's enough friction. It's a low amount of energy, but even the sound that it would be made would bring about the actual fire of some sort, the combustion of certain molecules. So that's crazy. Life would be difficult. Gasoline for your car would ignite as soon as it came in contact with air or with a lesser amount of energy. So we're not talking about necessarily no activation energy, but if there was a low activation energy as well. So activation energy is important. Why is it required input of energy? So that reactions don't just happen spontaneously. They happen under conditions, predictable conditions, albeit, but conditions nonetheless that we can rely upon, and it takes guesswork out of things, but also it keeps us safer, because we don't want all reactions occurring just spontaneously. We'll kind of want to have them dictatable, and we can put them off on our own. So it's why things do not need to happen. There needs to be some starting off, putting in of energy to get the thing rolling. Activation energy is like this hill to climb over. In order to sled down a hill, you got to first climb up the hill. That's kind of the best way I can illustrate this, is that if I want to sled down a hill, icy hill, I got to get up the hill before I can go down the hill. Pretty straightforward. I have to get to the amusement park so that I can ride all the rides. There's a cost to get the benefit out of get the benefit out of the investment, if you will. This particular activation energy doesn't show a nice smooth curve that we've seen before. It shows instead just the three different stages that goes on. There's this activated complex that acts as an intermediate space where the reactants are in sort of a limbo of reactants, products. Their identities kind of meshed together. That limbo would be called the activated complex, and it's very teetering on top of that thing. It's like putting something at the edge of a knife and having it balance, and then it's going to go one way or the other. Bottom line, there are 7 factors that we focus on that affect the rate of a chemical reaction. Remember, these factors increase the rate, make a rate or chemical reaction go faster. Okay. These 7 things can be manipulated in some form or fashion to increase the rate or decrease the rate if you do the opposite of what increases it. And these 7 factors cause the results of a reaction to occur, cause reactants to turn to products at a faster clip than they would ordinarily do under just basic conditions. They all lower the activation energy in some regard, or they increase the amount of collisions, or they increase the speed of the collisions. Some form or fashion, they are doing this, increasing the rate of reaction. And there are 7 of them. And before I go, I actually want to show you again those notes. 7 reaction rate factor. What is it? What happens? What are some examples? You'll have to dig that out a little bit, but there are 7 of them listed for you. You can fill that table. It can run to the second page. Doesn't matter. This is going to be your doc, of course. Before you print it, if you do print it, go ahead and give yourself some more space. You can print out some of those things and give you the space you need to write by hand, if you so choose. This is what you normally would just be writing by hand. So at least you have the ability to type it. And there you go. Why did I stop in the middle of my slides to do this? Because these 7 factors you're going to gather information on by yourself. Oh no, but what about? I just want you to tell me. That's right. Well, instead of you pausing every so often to write down whatever I'm talking about, they're pretty self-explanatory. I might touch on them later in the next video 5, but for now, let's just go straight into note-taking time. So pause the video now, collect these chemical reaction rates. I'm going to flow through it, but I'm not going to go very slow. We're just going to get done with this section, and then you're going to collect it by yourself. I normally have students do this in the classroom anyway. I put the slides around the room. I have you do it, and we verify some things. We talk about it. So pause right now if you haven't already. Get the notes of these slides. These slides are also attached to the Thermochemistry Day 4, Kinetics Day 1, right? It's attached to it. So just go look at these slides. Okay, go. And we're back. So we're going to follow back along together. Hopefully you got all those notes. We might revisit some of those details coming in video 5, but video 4 for right now. There we go. So remember that sheet the other day you drew your energy diagrams on? You may not, but I had you create a sheet where you wrote your endothermic and exothermic energy diagrams in this general area, endo and exo diagrams, and you took one side and cut it in half in your diagram. There we go. I'm back. So remember we had the one side where you cut it in half, Q&A on top, energy diagram on the bottom, and we drew in the energy diagrams. And then on the flip side, I had you draw these 4 boxes. Well, get that page out or remake it, I suppose. I mean, you might have to go back and remake your energy diagrams. But we want to have our labels just like this. Now is the time we're going to take the notes on this. So pause, get it out, find it if you need to. Otherwise, here we go. Remember the energy diagram. We've already sketched and labeled this. We said as the course of the reaction, I'm going the wrong way. Course of the reaction goes forth. The energy must go up in order for reactants to turn into products, must overcome an activation energy. For the moment, they're in a new state called the activated complex, and then they turn into products as a result of that. Chemical equilibrium is a reaction state where both reactants and products are present, but the concentrations of both are no longer changing. Chemical equilibrium in chemistry land means that the reaction has reached an equilibrium state, meaning as much of the reaction that's going to occur has occurred, and now it's kind of at the state where the formation of products is slightly constantly changing from reactants to products, or products backwards to reactants. And as it's kind of balancing out that about as many products are being formed as reactants, because there's way more products than there needs to be than there are reactants. That's called equilibrium, when the reaction has gone fully taken place and it kind of settles back out. Think of on Black Friday in really busy metropolitan areas, when malls or Walmarts or whatever that have Black Friday deals open up. But before they open up, you've got lines outside the door. People are going to pile in. I guess before the days of COVID, of course. Well, picture some old movies with the newest, hottest toys, at Toys R Us or whatever. People are piled outside the door. As soon as that door opens, 5 a.m. or whatever, the crowd rushes in. Well, all at once, that's the reaction occurring. Equilibrium is not reached, obviously, at that point. We're not talking about that. We're talking about once that big wave goes in and people are mostly entering. They go about their time, run through the process of buying things, and they leave the store. As those who are leaving are now equal to the numbers who are now entering, and the wave generally shows a vast population of people inside shopping and or buying. They're either entering, shopping, or buying, or leaving. As soon as that number kind of equals the number who are leaving, coming in and out at some point later on in the day, they're so busy on the inside that for every 2 people who leave, 2 people come back in. 2 people leave, 2 people come back in within, say, an hour. That would be considered equilibrium. Even though there's a vast, larger number inside than outside, that's talking about the end point. That's talking about the number of products formed. We're not worried about products versus reactants. We're talking about how many products are being formed versus how many reactants are being formed, in reverse. So how many people are coming into the store versus how many are coming out of the store. When the numbers are about equal over a certain period of time, that's when you reach quote-unquote equilibrium. In chemistry, we're talking about once all the mass amount of products are formed, some of the products will form back into reactants, and the reactant will form into a product, and then product to reactant, and then reactant to product. And they're just happening at the same rate, 1 to 1, or whatever however long it would take for one-to-one to occur where one happens and the other happens in reverse. One happens and the other happens. That, when it's doing this trade-off sort of thing, is when you're in what's called equilibrium. The forward and the reverse reactions are occurring at the same rate. Okay, make sure you're putting this down in the notes section. Because of this, interreaction in equilibrium is considered reversible. Consider the decomposition of N2O4, dinitrogen tetroxide, into two NO2s. At equilibrium, the rate of the forward reaction, Kf, K is the rate constant for the forward reaction, Kf, Kr, reverse, is the rate constant for the reverse reaction. That means the forward stuff is happening at the same rate as the reverse stuff. There, it's a one-to-one trade-off over whatever period of time, an agreed period of time. So, that's equilibrium. Is it the forward? Let me say this. The forward is equal to the reverse. Rates. The rate of forming a product is equal to the rate of forming a reactant. That still can mean there's way more products than reactants. The bottom line is the rate of forming is a 1-to-1, 1-to-1 rate. Right, one is forming, one is unforming. One is forming as one is unforming. That would be considered equilibrium. When you make tea, you stick a tea bag into water, hot water. The water washes in, some of the sediment that makes the tea bounces out through the membrane, and then most of it rushes out early on, and then eventually some is going back and forth within the membrane. There's a period of time, normally between 4 and 9 minutes, depending on the type of tea, that this occurs, and after about 4 to 9 minutes, you're going to get as strong as you're going to get based on the amount of water and the amount of tea that you have in the tea bag, based on how much can be dissolved or suspended in the solution in any way that makes your tea. So that would be this point of equilibrium. That's why it's no point in actually letting things stew much longer, steep much longer than they can, unless you're going to keep the temperature rising up, because it can steep more out of the tea bag. Anyway, equilibrium is a reaction that may take some time to reach. It takes time. Of course, the forward reaction starts quickly and occurs usually all at once, mostly at once. But then the reverse begins at a slower rate, and it must happen after most of the forward reaction has taken place. Most of the products have occurred. Eventually, forward reaction can equal the reverse reaction until you reach this equilibrium state. Here's a little graph that demonstrates this, that as time goes on, you have forward reaction happening at a decreasing amount of rate, and the backward reaction happening at a decreasing amount of rate until they meet in the middle and they're happening at the same rate. Can you think of a real-world example of equilibrium? I've kind of given you some, like a Black Friday store opening up at opening hour, or tea bag. Can you think of another one? Think of it and let me know later in class. Remind me, because I'm not going to remember to tell you to ask for it. So remind me. Equilibrium conditions. There are 3 take-home messages regarding equilibrium. At equilibrium, concentration of reactants and products no longer change with time. So the formation of a product is happening at the same time as the formation of a reactant. There's no new of either one. They're trading spots, basically. It's +1, -1, +1, -1. For equilibrium to occur, neither reactants nor products can escape. You can't necessarily, they can't fall out of the reaction. If they fall out of the reaction, then that can actually move the reaction in the direction that is being pulled. That's another principle we're going to talk about called the Chatelier's. At equilibrium, a particular ratio of concentration terms equals a constant called the equilibrium constant. That's called the K constant. Notice this is an uppercase K. The rate constant is a lowercase k. Kf forward, Kr reverse. K, capital K, relates the forward K to the reverse K in an interesting relationship. This is called the equilibrium constant, sometimes just called K, sometimes called K of the reaction of a certain element or product or molecule. It's usually called K with a subscript EQ to mean equilibrium constant. K is a typical constant letter. So equilibrium constant is related to the rate laws of the forward reverse reaction. So let's take the reaction. Kf is the forward reaction takes the reactant into O4, and the Kr reverse into O or NO2. The superscript is 2, and this is because the coefficient of the formation of NO2 was 2. Coefficients become superscripts, which means to exponents when you're doing the math of the concentrations. So if I have a concentration, this literally means Kf is the forward rate constant, which is a certain value, is equal is times the concentration of N2O4, how many reactants there are. And that is set equal to Kr, the reverse constant, times the amount of NO2 raised to the exponent, which is its coefficient in this case. So when these two values are equal, Kf times the reactants equals Kr times the products, that's when we've reached equilibrium. And if we rearrange the Kf and the Kr to be Kf over Kr equals the, so we divide by Kr here and we divide by N2O4 over here, we get the products on top over the reactants, where we put the equilibrium, where we get the coefficient as the exponent on whichever part there is, and that equals the equilibrium constant. So we'll look at a practice one in a second. So, but first, you're like, wait, K? What is a K? K is this rate constant. I mentioned it before. It's a number associated with each reaction that tells the speed, the rate by which products are being formed. So we say that the change in concentration of the products, that C means concentration, the brackets tell you concentration. The change in this concentration over time, how fast that's occurring, is equal to the KT value, K of time, the rate, the K value in terms of time, of the products, of the product formation, product A raised to its coefficient M, and B, another product raised to its coefficient N. Of course, as many products as there are necessary, we could add letters here. The next one would be C and O, right? If we had a third product being formed. In this case, two products are typical. So A product and a B product, and M coefficient that goes with the A, and N coefficient that goes with the B. Make sure you understand what I just said right there. So let's take a general reaction where you have, with easier subscripts, we have A reactant reacts with a B reactant to form a D and an E product. A is the coefficient for A, B is the coefficient for B, D is the coefficient for D, and E is the coefficient for E. To find the Kc, also the other way to report or express equilibrium constant, is we take, let me pause for a second. We take the product, the concentration of the reactants and products, and we write them in terms of their concentration. Product raised to its exponent times product raised to its exponent divided by reactant raised to exponent times reactant raised to exponent, and creates a simple math problem to determine the equilibrium constant. You're going to practice this in the in a Savas Realize classwork assignment. It's super easy, no tears, no fears. Let's go. So what is the Kc for this reaction? You can try this on your own. You can pause now and try it on your own and then compare it to mine. Coming now. Pause now if you don't want to see it yet. Oh. I'm not going to get a chance to write it. This one is, well, I'm going to do it on here as best as I can. This is not going to go. Yes, it will. I'll do it right here instead. Okay, so we have Kc or Keq. I'm going to use EQ because that's my favorite. Keq equals line in between, because we're going to take products, NH3, bracket, over a raised to its exponent, or raised to its coefficient, 2, over N2. Its coefficient is 1, so it does not get a raise to, times, we just put it next to it, the other reactant, H2, with a 3 coefficient, so 3 exponent. That is the Keq value, or Keq constant. Now, writing is one thing, and then what they would have to do is provide you some details. They would need to provide you the amount, concentration of NH3, the concentration of H2, the concentration of N2, and they'd have to all be in the same terms. They usually would be if they ever gave you this type of problem. And then you could take this number and square it and divide it by this number times this number cubed, and then you divide it all out, do all the math that's present, and you get a Keq value that would be between 0 and 1 or 1 and up. And that gives you two different situations going on. And we'll kind of point out those as we go. So, gas and equilibrium, we can work with gases. There's a little bit different things, just like molar volume of gases doesn't use molar mass. We use a molar volume at 22.4. Gases make things a little bit more complicated. So concentrations are important for gases. What's important for gases are the pressures of each component, the partial pressures. So the pressure of the reactant, or excuse me, pressure of the products raised to their exponent coefficients over the pressures of the reactants raised to their coefficients gives us the Kp, or the gas equilibrium constant. So what's the Kp for these two gases? Can you do it? It would be bracket NO2 raised to the 2 over bracket N2O4 raised to nothing. It's just be a simple division problem. All right, what's the Kc for this value? In this case, they're giving us the Kc expression would just be COCl2 in brackets over CO in brackets times Cl2 in brackets, no exponents because no coefficients, and that would be set equal to 4.56 times 10 to the 9. Because we said that the Kc value is larger than 1 at equilibrium, which are there more of? Products. It turns out there are more products if the equilibrium constant is above 1. If the equilibrium constant is between 0 and 1, there are more reactants at the point of equilibrium. Also, we would say 1 or more is the equilibrium constant. The reaction occurs faster towards the products in the forward setting, and the higher it is, above 1, it occurs faster towards the products. If the KEQ is between 0 and 1, the smaller it is, the slower it goes. Smaller KEQ, the slower the reaction occurs because it's going more towards the reactant side as it proceeds. If the K is greater than, that literally means in chemistry way more than 1, equilibrium lies to the right and products dominate. If K is less than 1, that means way less than 1, or between 0 and 1 technically, it lies to the left where reactants dominate. There are more reactants than there are products. So, worth looking at some of these things. So what is Kc in the reverse direction? This shows the forward. Kc is 0.212. In the forward direction, we would have NO2 on top, brackets raised to a 2, over N2O4 on bottom, bracket raised to nothing because its coefficient is 1. The reverse just flips those things on its head and then inverses the 0.212. But we leave it alone. Le Chatelier's principle. This is where actually we'll pause video 4 for right now. We'll touch on this in greater detail, maybe do it a part 2 or in video 5. One way or the other, it's going to be the conclusion of this video. But Le Chatelier's principle is a very cool thing that if you shift a component of the reaction, it drags or pushes the reaction in that direction. Fun concept, coming later, not today. See you. Thanks for watching. Go Dog.